Hello and welcome to this week's edition of Labrats. So last week we did an experiment where we used alum and Epsom salt. So alum, we learned, is a pickling agent, so we use it in making pickles. It's what gives pickles their crunchy snappiness. And we used Epsom salt, and Epsom salt is essentially an additive that you use for bath salts and having baths. And we essentially made supersaturated solutions. So a supersaturated solution means that you can't possibly dissolve any more of that salt in the water without it basically crystallizing or falling out as a solid at the bottom. And we made crystals out of that. So I gave you two things. For the Epsom salt, I told you to use a paper clip that would maybe grow crystals on it. And for the alum, I gave you an alum seed crystal. So a seed crystal is a crystal of alum that you put in the solution and the alum will grow on it. So the alum crystal that you should have been able to grow should have looked something similar to this, so a nice big crystal. And the Epsom salt, you should have had an experience like you see in this jar where the crystals actually did not grow on the paper clip at all. And I did that to you on purpose. So you may be thinking, well, why didn't this experiment work? And it's because essentially, I was trying to get you to think about why you would have your crystal grow on a crystal itself, but not on the paper clip. And that's because essentially nature's a little bit lazy. So when you have a seed crystal, the alum, for instance, wanted to naturally grow on that seed crystal because it already had the crystal structure that the alum makes up when it forms a crystal, whereas the paper clip doesn't. So the paper clip is just a smooth steel surface. It doesn't have a crystal structure, at least not a crystal structure like the Epsom salt wants to naturally grow in. So on the bottom of your jar, you would have had a bunch of little leftover crystals that would have been formed on the bottom of this jar, and the Epsom salt was more attracted to growing on those little tiny leftover crystals than it would have been to growing on the actual paper clip itself. So you ended up with a whole bunch of crystals at the bottom. So that's why that happened, essentially. So I wanted to get you thinking about, this experiment didn't work. Why didn't it work? And I gave that to you because that's actually how science works. Sometimes the most profound discoveries that are made by doing things that you never expected to have a result from, or doing a certain experiment and then you get a completely different reaction. And so I wanted to kind of give you a feel for how science can be sometimes. And essentially the point of this is that there's like 9,000 different minerals on the face of the planet. Only about 36 of them occur naturally in rocks. And I just wanted to give you a feel for how crystals grow and that different substances will produce different crystals because they're different materials. So this week, I actually am having you make something called hot ice. So you use a product that's called sodium acetate. And sodium acetate you can actually make naturally in your own kitchen. It's a non-toxic solution. You basically create it by mixing 4 cups of vinegar with 4 tablespoons of baking soda, and you produce a reaction that produces, the liquid becomes sodium acetate, and it reacts and foams to create carbon dioxide that's released into the atmosphere. So that in itself is actually a really neat chemical reaction that you can perform safely in your own home. But then you can take that sodium acetate and you can boil it down to basically being the super concentrated, a hyper concentrated version of sodium acetate. And you take that boiled solution and you can put it in the freezer and it super cools it. So what supercooling means is that it goes from being super hot at its boiling point to being below its freezing point. But because it's such a shock to the solution that's experiencing that it doesn't actually freeze. It kind of stays in this like super cold. It's colder than the liquid should be. It should be frozen, but it's not frozen because it goes through this like shock period basically. So I also boiled a little bit of that liquid down for you to produce some seed crystals. So these are the same types of seed crystals that I gave you for the alum crystal experiment. So what you do is you take your sodium acetate and you boil it, and then you put it in the microwave and heat it up, and then you put it in outside because it's minus 20 now, or you can put it in your freezer for about half an hour, an hour. It depends on how cold it is. And then you can take one of these little seed crystals that I gave you, and you can just put it on the bottom because this is what kind of kickstarts the reaction to start. And then you can take your sodium acetate, which is still in its liquid form, and you can pour it out. And it'll actually slowly start to become a crystal that'll form. So you can see that it's slowly starting to form bigger crystals here. So that's essentially how this experiment works. So, and now that I've jostled this around, it was actually a liquid before, but I jostled it around a little bit, and it's become all of these like super spiky crystals that you can see here. So depending on how concentrated your solution is and how cold your solution is, it can actually form this really, really tall crystal that you can pour out and make. So my solution, it's been sitting outside here, so it didn't quite get the dramatic result that you can get by doing this experiment, but you kind of get the idea here. You can actually get it to the point where it can grow quite a tall crystal. And essentially what this does is because it's in this state that's super saturated and super cooled, as soon as you pour it out, it actually instantly freezes and creates this instant crystal. It's a crystal essentially. And it's actually creating a exothermic reaction. So there are reactions in chemistry that produce heat, and there are reactions that take away heat. When ice freezes, for instance, that is a reaction that takes heat away. That's why ice is cold. Whereas this reaction, when it's done properly, it actually produces a little bit of heat. So it actually produces a bit of a hot crystal. So if you were to touch it, it'd be a little bit warm to the touch. And so this really, you know, it shows you a number of different things. It shows you crystal structure, it shows you supersaturation of solutions, it shows you supercooling and crystallization. So there's all of these different things in this experiment, and it's just kind of a cool visual experiment. So you can give that a try it out, and you might need the solution that I did give you, that I made. You might need to boil it down a little bit more to get it concentrated enough. It would have depended on, you know, the different solutions that I mixed, because I had to do not multiple batches of it. So you can get a parent to help you with that, or an adult to help you with that. And if you want to take pictures of it and show it in the comment section of this video, that would be great. And I'll see you next week.